Hi everyone, welcome back. I hope you managed to catch a short break. We will continue with Dr. Bosung Lee, Solutions Architect Director at Rescale. And the title of his talk is Simulation Cost Analysis on Rescale HPC Cloud. Dr. Bosung, please go ahead.
Hello everyone. Thank you for joining my presentation, and I appreciate for the presentation champion SC Asia. My name is Bosung Lee, and I'm in charge of solution architect team and the customer success team in Rescale Korea. Today, in this presentation, I will talk about the total simulation cost on the Rescale HPC Cloud environment in terms of cloud hardware cost and the simulation software license cost together. In this presentation, we will discuss about some topics. At first, the background and objectives of this presentation will be explained. Next, I briefly introduce the Rescale HPC Cloud. After that, the component of the simulation cost will be discussed in terms of the hardware infrastructure cost, and the commercial simulation software license model will be explained. And using some example case, such as Siemens Statistician Plus and ANSYS Fluent, the total simulation cost analysis result will be compared using various Rescale HPC Cloud hardware. Finally, we will see how HPC hardware and the simulation software combination can reduce the total simulation cost. Usually, the total cost of ownership analysis of HPC infrastructure has been performed about the hardware infrastructure cost only. In this infrastructure, server, storage, interconnection network, and some HPC management software and the job scheduler are included. By the way, the real simulation cost should be calculated with not only infrastructure cost, but also with the simulation software cost together. As we know, except in the case of open source software, most of commercial simulation software is very expensive than hardware cost. Because of this high commercial license price, most of users' simulations are limited by not only the number of cores, but also the number of licenses. For this reason, in the TCO analysis of HPC infrastructure, especially in the cloud HPC infrastructure, should be performed using the hardware cost and simulation license cost together. Therefore, in this presentation, the total simulation cost is defined as the sum of HPC hardware cost and the license cost. Also, this simulation cost is dependent on the simulation time. It means that if we can reduce the simulation time, we can save the total simulation cost also. From this simulation cost point of view, I'm going to compare total simulation cost using Statistician, Fluent, and open source software on various Rescale HPC infrastructure hardware. And we will discuss how to reduce the total cost of simulation in the HPC cloud environment. Before start, I will explain Rescale HPC Cloud briefly. Rescale is the turnkey-based HPC SaaS service, and we are based on the public cloud infrastructure such as AWS, Azure, and GCP, Oracle, and IBM. And on this public cloud base, hundreds of simulation software are installed with the user-friendly interface, such as a web interface and the command line interface and the RESTful API. Using the Rescale web interface and the CLI and the RESTful API, the user can set up and run and carry out their post-processing of their simulation result very easily in Rescale HPC Cloud. Next, let me introduce the simulation workflow in the Rescale HPC Cloud. After set up model in the cloud or in the user's local workstations, the user upload the mesh and the input file to Rescale HPC Cloud. After that, next, the user select the software and the license for their simulations and select the suitable hardware and the number of cores in the Rescale platform. After that, the submitted job will start without waiting for allocation of hardware different from on-premise HPC queuing system. When simulation is ended, the allocated cloud hardware is automatically stopped and the result files are stored to the user's object storage automatically. Also, if the user wanted to process the visualization, the user can perform the post-processing on Rescale HPC visualization system without downloading large output files to their local workstations. This slide shows the core types of Rescale HPC Cloud. We call the cloud instance as the core type, and they are named as the mineral names such as emerald, jasper, ruby, or diamond, etc., etc. In addition to the pre-installed simulation software, as mentioned before, the user can choose the proper hardware type for their simulation in Rescale HPC Cloud. As you can see, Rescale provides the general price performance core types, and for example, for large memory required simulations, the user can choose the high memory core types as below, as shown. Also, low latency interconnector-based core types such as InfiniBand or AWS EFA are also provided. In addition to various CPU core types, for AI ML applications, GPU core types are also integrated together already. These core types are continuously added and increased according to the hardware advances, and the public cloud provider adopted the new hardware instances. And using the Rescale cloud, because the Rescale HPC cloud is based on the various public cloud, users need not waiting for allocation of hardware resources different from on-prem with HPC cluster. And also, depending on the type of simulations, the best optimized hardware can be used at the same time. For example, GPU applications can be submitted to GPU core types, and the high memory jobs will be run in the high memory core types at the same time. To do this, the user's simulation time and the cost can be optimized in Rescale HPC Cloud very easily. Next, we will talk about the simulation cost more deeply. As you can see, the general simulation cost on HPC Cloud is composed of 4 key factors. The first factor is the cloud infrastructure cost, which includes computer hardware, memory, networking, and the storage systems. In the cloud environment, it is the IaaS cloud cost, and in the case of on-premise HPC, the on-premise hardware cost. In the infrastructure cost, sometimes system software such as job scheduler needs to be included. With the infrastructure cost, support and the maintenance cost and the HPC implementation cost should be included. Generally speaking, until yet, HPC TCO analysis has been performed by these all 3 factors. However, for simulation cost analysis, in addition to these 3 factors, software and application license cost should be included. Because, as mentioned before, the software license cost is much higher than that of the other 3 factors, such as infrastructure or any other system softwares. In this slide, we will take a look at the license cost model more deeply. Traditionally, in the on-premise HPC environment, the perpetual license or annual list license model is widely used. Most perpetual license models are one of the three models. The one is the model based on the number of calls. The typical and widely used type of this license model is ANSYS license. For example, almost ANSYS software license is composed of the solver license and the number of HPC pack licenses. And the number of HPC packs increases as the number of calls increases. The typical model based on the number of concurrent simulation is a StarCCM plus power session license. In the StarCCM power session license, there is no limit in the number of calls, but using one power session, the only one simulation can be possible. It means that if the user wanted to run two 10-core simulations at the same time, this user should have a 2 power session license. But for 1,000 calls per one simulations, the only one power session license is sufficient for StarCCM license. Meanwhile, as the HPC cloud becomes widely used, the ISV vendors also provide the on-demand license for cloud usage. The on-demand license model is charged based on the time of usage in addition to the number of calls or the number of concurrent simulations. For example, ANSYS elastic licensing model is calculated by the above complex formula, and it named as AEC license. But it is basically based on the number of calls and the simulation time. StarCCM Power On-Demand license has the same license scheme with the Power Session license, only except it is charged by the usage hour. Likewise, the perpetual license cost can be calculated according to the usage time. In terms of perpetual license utilization should be increased to reduce the cost. For example, if the license utilization is 50%, the real license cost will be twice than the purchase cost. Anyway, though each simulation software has a different charging scheme, the license cost is proportional to the simulation time and sometimes proportional to the number of calls or number of concurrent simulations. Therefore, if the simulation time decreases, license cost also can be decreased. This slide shows the various core types and the price in Rescale HPC Cloud. The price in this slide are sample, and this price are variable on the contract size, date, and the cloud regions. Anyway, as I mentioned just before, whether the perpetual license is used or on-demand license is used, to reduce the license cost, the pay-test core types may be useful. As shown in the table, Rescale suggests various core types and they have different performance and price. For example, some core types has a very high clock but very expensive. But the price of performance core types has the lower price and the moderate performance. Anyway, therefore, in some cases, the higher price core types may result in the lower total cost because the execution time is less than the other cheap core types. For example, using the higher core types and reduce the simulation type, the total hardware cost can be reduced. But sometimes the better price performance core types can show the lowest cost for some applications. Therefore, to achieve the optimal simulation cost, hardware performance and the price and the simulation license model must be comprehensively considered. In this section, based on the simulation cost, we mentioned before, some examples of simulation cost analysis result will be discussed. At first, statistician plus simulation cost analysis result is shown. In this case, 28 million cell model was used and the execution time is calculated until 2000 iterations are compared. The estimated POD license cost is $32.5 per hour is used. In this case, the execution time is fastest when the at-night core type is used, but the at-night unit price of at-night is more higher than the other core types. Otherwise, the hardware only cost is lowest when the JESP is used. JESP is AMD ROM architecture and very cheap, and it has the moderate the performance. This result is due to the hardware cost is dependent not only on the unit cost, but also dependent on the execution time. So if the execution time is reduced, then the total cost can be reduced, as I mentioned before. On the other hand, if the license cost is added, the total simulation cost is the minimum when the at-night core type is used. Because when using at-night core type, the simulation time is the lowest, so statistician cost may be reduced. In this statistician POD license case, the license cost is independent on the number of cores in the simulations. Therefore, the total simulation cost is only affected by the hardware cost and the simulation time. The next case is the NC's CFX simulation cost. Oh, sorry, this is the NC's Fluent simulation cost mistyped. The different from the statistician plus, NC's Fluent license cost is dependent not only on the simulation type, but also on the number of cores by the very complex AEC formula. In terms of the elapsed time, just for 120 cores show the fastest result than other core types. But however, when the license cost is added, a peridot 44 cores shows the minimum simulation cost, because this is due to that the NC's license cost is affected by the number of cores used. So if when the NC's Fluent is used, if the user if the simulation is using the many cores, the license cost may be increased. So we can say that the optimized simulation cost for NC's application should be calculated in the view of simulation time and the number of cores in addition to the hardware unit cost. Next, the third case is the simulation cost comparison when different simulation software is used for the same simulation model. For this comparison, drive-aware full-car model was used, and for this drive-aware full-car model, NC's Fluent, GMAP's Statistician Plus, and OpenFOAM-based solver, which is named as Baram, was used for the same mesh. To minimize the effect of the simulation algorithm, in all three cases, the solution schemes and the spatial discretization scheme will coincide as much as possible. All three simulations were performed on the same core type on Rescale, and the Rescale JESP core type from 60 to 2000 cores were used. This is the boundary condition and the flow condition for the comparison. In this slide, the comparison result is shown. Left upper graph shows the drag coefficient compared to the experimental result. This is the independent on the simulation cost, but the simulation analysis, simulation accuracy was compared. In all three solvers, the range of drag coefficient is similar to the experimental result. Work clock time for 20,000 iterations is shown in the left bottom graph. In this graph, when single load 60 cores is used, the Fluent shows the lowest work clock time. But when 4 nodes were used, 4 nodes means the 240 cores used, Statistician Plus shows the slightly lower execution time than Fluent. In free software, the scalability is reasonable. In each software, the hardware cost is not much different as the number of nodes increases. This is due to that the cloud hardware cost characteristics. As the number of cores increases, the cloud hardware cost increases. However, by increasing the number of cores, the simulation time is reduced. So the total hardware cost is not much changed from 60 cores to 240 cores. Due to the above cloud hardware cost characteristics, the license cost can be reduced as the number of cores increases because the simulation time will be decreased. As I mentioned before, if the simulation time can be reduced by using the many cores, then the license cost can be reduced. So in this result, finally, total simulation cost will be reduced also. Of course, if the open source software is used, there is no license. So the simulation cost can only compose of hardware cost only. Next. In the last case, I compared the cost of AI/ML case using various GPU core types. The ImageAl object detection code was used in this object detection algorithm, and this algorithm uses only one GPU and several CPUs for detection. So the frame rate is composed of the portion of CPUs and the GPU performance also. In this case, different from our expectations, the T4 GPU with the 4 CPU, 2 CPU in the slide is mistyped. Case shows better performance than other VBAC GPUs. And the previous generation V100 in Aquamarine V3 shows better performance than the latest Dolomite V100. This is due to that the performance of the object detection code used in this comparison is affected not only by the performance of GPU, but also by the CPU performance. In the Aquamarine V3, 6 CPUs are used but the 4 CPUs in Dolomite is used. So the CPU portion is CPU portion is affecting the total frame rate. So Aquamarine version 3 shows the better performance than Dolomite. In terms of the simulation cost, T4 GPU core types sold much lower than other core types. This is due to that the T4 price in the public cloud is much cheaper than the other V100 GPU core types. Next, final slide. In previous slide, some expectations of simulation cost comparison were shown. In summary, to reduce the simulation cost, the type of cloud hardware simulation software license model and the execution time must be optimized. However, this optimization is not easy for each simulation cases and for each researchers. From the point of optimization, to reduce the effort for optimization, Rescale provides the performance dashboard and optimization features. In Rescale, using previous simulation job data points such as execution time, cost, and core types, the best price performance core types will be suggested in the platform. Okay. In this presentation, we talked about the total simulation cost analysis on the Rescale HPC Cloud environment. Concludingly remark, we found that the simulation cost is composed of various factors such as cloud hardware cost, simulation license cost, and the simulation time. Therefore, to minimize the simulation cost, the optimal cloud core types and the number of cores must be selected. In addition, simulation software license model must be considered per cloud simulations. This optimization may be hard work for each researcher, but in the Rescale HPC Cloud, by using various core types and the performance optimization dashboard, the simulation cost optimization may be easily achieved. Thank you very much. Any questions?
So thank you, Dr. Bo-Sung Lee, for this very insightful talk. It's good to remember that when dealing with the cloud, there are a multitude of costs that one should account for. So it's not just the resources, there are also the various licenses, and it was interesting to learn about Rescale solution to this problem. Our next speaker is Mr. Shun Utsui, Senior HPC Solutions Architect at AWS. The title of his talk is The Hybrid HPC Approach. Extend your on-premise resources to AWS. Shun, the floor is yours.
Thank you, Yurine. Hope you can hear me. Yeah, okay. All right, so hi, my name is Shun Utsui. I'm a Senior HPC Solutions Architect at AWS. I've been with AWS for about 8 months now, but I came from a very traditional HPC, on-premise HPC background. And I've been in the HPC market for about 13 years, but most of the work I've done is on-premise. But I'm a very strong believer in the potential of cloud, and that's why I came to AWS. And today I'm obviously going to be talking about hybrid HPC. But in order to set up the context, I would like to start with why HPC on AWS and why you might want to consider moving some of your workloads to AWS. So how does AWS think about HPC? We think about HPC like we think about any other customer. We're very customer focused. We start from the customer and work backwards. We look at the problems that our customers have and try to address these issues by building new solutions or services. We also want to maintain a long-term relationship with our customers. So once they're on board AWS, we help them to reinvent their solution to make their solution even cheaper and more performant. Now, there's an interesting study done by Hyperion Research, whereby they discovered that 72.8% of organizations that use on-premise HPC reported delayed or canceled jobs. Now, that's kind of a shocking number. And it could be because you have a full system in your on-premise system and your job never gets running. Or it could be because your system administrator canceled your job just because they thought somebody else's job is higher priority. And we refer to these things as lost innovation. Now, with on-premise HPC, you could also end up with outdated technology. If you think about it, a typical procurement cycle for an HPC system is 5 years. And 5 years is quite a long time if you compare it against technology updates from CPU or GPU vendors. There's also the aspect of technical debt, whereby you're adapting newer algorithms to existing infrastructure, which could be an old one. So what can AWS do to address these issues? And a lot of the time, when people talk about HPC on cloud or HPC on AWS, the focus is on cost savings or total cost of ownership. But the deeper you dive into the capabilities of AWS, you would notice that it's not just the TCO that is bringing you a benefit. There's also things like staff productivity, operational resilience, and business agility. And whilst the TCO is obviously important, the elasticity of AWS brings you a lot of other stuff as well. And those are, and the things that you see here on the right are the most compelling cloud benefits. Now, I use the word elasticity, and let me explain what I mean by that. So if you look at this diagram here, you see a typical on-premise infrastructure setup. Now, the colored boxes here represent the jobs that are submitted by several users. The on-premise resources have finite capacity, so users will have to wait for a longer wait time. Now, with the current job schedulers, they do support functionalities such as backfill. And these functionalities are great. But it could also mean that you could have very important jobs in your system, but you could also have jobs that are not so much important, but are just there to fill up the system for efficient use. Now let's have a look at how that looks on AWS. AWS allows you to flexibly scale, meaning that if you need the resources, it allows you to scale beyond your expected needs. And on the other hand, if your users are on holiday, for example, or they might be writing papers, and they might not need an HPC system all the time. And during those times, let's just shut down the resources that you don't need so that you don't have to pay for it anymore. But that doesn't just mean that you're paying less. You're also getting the resources at the time you want. You're not waiting for anyone else's job to finish to get your job done. I would also like to point out that with AWS, you would get access to an evolving ecosystem of services. So for example, if you don't have the latest GPUs available on your on-premise system, you could do that on AWS. So you see that AWS is not just about TCO, but it's about bringing you business value. But how do our HPC customers migrate their workloads to AWS? And the level of effort differs because all of our customers have different requirements and different needs. But we're here to support all of our customers. And we try to make the cloud onboarding journey as easy as possible. And we try to immunize our customers with whatever is available to do so. So here, I do have a typical view on how a cloud onboarding journey could look like. Normally, you would start with an experimentation or some kind of POC that will formulate a foundation. And once you have that foundation, you will move on to migrating your workloads to AWS. And that could take many forms. Like, for example, you could think about a lift and shift approach whereby you replicate your on-premise system on AWS and then migrate your workloads from on-premise to AWS. You could also think about a cloud-native approach whereby you actually start building AWS cloud-native architecture using cloud-native services such as AWS Batch or Elastic Kubernetes Service so that it matches your whatever you want it to do on-premise as well. And the final step is to keep reinventing after you have onboarded AWS so that you can get your infrastructure on AWS even better in terms of cost and performance. But let's stop here for a second. What about customers who can move all their entire infrastructure or their entire workloads to AWS or to cloud? And you might have already invested millions of dollars into your on-premise data center. And for those of you who are in a similar situation, it might make not a lot of sense to make a transition fully from on-premise to cloud. But wouldn't it be nice if you can keep actually your on-premise infrastructure on-premise, but also leverage on the benefits of the cloud? And that's why we have been thinking about a hybrid strategy. A nice EnginFrame in AWS HPC connector gives you the ability to integrate your on-premise HPC environment with AWS. Now, some of you might be already familiar with nice EnginFrame as an on-premise portal because it has been there for quite some time. It's popular amongst customers who use it as a workflow engine. You can schedule job flows around it and manage on-premise infrastructure. But we saw a lot of demand signals from our customers who wanted the same thing on AWS as well, because they didn't want to have a separate workflow for on-premise and cloud. And that's why we built the AWS HPC connector, which is a plugin to nice EnginFrame, which enables you to do the integration. Now, I'm going to go into the technicalities of nice EnginFrame and AWS HPC connector. But before doing that, let me talk about the use cases that we think are applicable for the solution. Now, the first one is cloud bursting. When there's a high demand on-premise, just burst your jobs into cloud. It's quite simple. The second use case is workload migration. And the nice thing about nice EnginFrame is that it provides you a single interface for both your on-premise and AWS resources, meaning that your system administrator can change the underlying resources from one to another without disrupting the UI. So for example, if you have a system maintenance coming up on-premise, you could actually change your underlying resources to AWS without disrupting the UI for your users, even during the system maintenance. The third use case is cloud-only HPC. And we understand that cloud is still new to a lot of HPC customers. But what nice EnginFrame enables us to do is to make AWS more accessible to HPC administrators and end users who might not be familiar with how to set up an HPC system or an HPC cluster and run jobs on it in cloud. And the great benefit about that is that you can really leverage on the benefits of cloud. So for example, again, if you want to access the latest FPGAs, for example, you can do that through nice EnginFrame. You can, if you want to test your workloads using ARM CPUs, that's possible with our Graviton instances. So what exactly is nice EnginFrame? And to start with history, AWS acquired a company called Nice Software in 2016, which was the original developer of the software Nice EnginFrame. And after we acquired the company, we developed it even further, and we made it available on both on-premise and AWS. It's an easy-to-use interface to get started running your HPC workloads, and it's highly customizable at every level. Now, here you see a typical workflow for a nice EnginFrame setup. And you would start with configuring and creating a cluster, then move on to setting up your users and your interface, and then you would set up application templates for your users. You would give them access to those templates, and once they have access, your users will start submitting and managing jobs through it. It has flexible integrations with most of the schedulers that you can think of, and it integrates very well with a lot of user authentication systems. Nice EnginFrame enables the full life cycle of engineering workflows. So let's say a system administrator has already configured an application template for the users. The users would then get a very nice interface where they have to just put in the parameters for submitting a job in the GUI, and then they will be able to submit their job into an HPC cluster. Now, once they submit a job, they will have the ability to monitor their jobs through the same UI. And they would also be able to see where their files are written into and stuff like that. Now, once their job is finished, they'll be able to monitor their output or their results on the same interface. And if they don't like the results, they can just go back to resubmitting their job with updated parameters. to refine their results. Now, the great thing about Nice EnginFrame is that it allows the system administrator to customize who can see what. So for example, here on the left-hand side pane, you see general resources, and those are things like your job status, your files, and stuff like that. And these are common to all of your users. But then you also have an application-specific grouping, which can be customized by the system administrator. You also have the visualization part, which allows your users to access your visualization resources. So coming to the main part of the application template, you see that there are runtime job parameters and application parameters. And these are very carefully designed by the systems administrator so that the users only see the things that are related to their to the research itself. And the key takeaway here is that users don't need to know anything about job schedulers or how to write a job script for a specific job scheduler. And you might be wondering how that's even possible. And it's possible because there are two important scripts that you need to configure when you are creating the application template. And on top here, you see the action script, which is responsible for submitting a job to the respective HPC resources. And in here, you could define or write a lot of things. For example, if you want all of your users to do some pre-processing work for a specific application, you can do that in the action script. If you want one of your users, for example, to use a specific node, for example, then that is also possible on the action script. Then below, you see the job script, which is going to be responsible for executing the job on the HPC resources. Now, the thing here is that you can define environment variables. And these variables will take the inputs from what the users have specified in the GUI template. And depending on that, the job will run on on how you would have configured your action script and job script. All right, so on to the AWS HPC connector. And AWS HPC connector is something that we have just released in December 2021. It's a plugin to Nice EnginFrame, which enables you to integrate your on-premise resources with AWS ParallelCluster. And if you're not familiar with AWS ParallelCluster, it's a one-stop shop for you to be able to deploy an HPC cluster on AWS through a single command. It gives you the ability to deploy a similar cluster to your on-premise setup. So for example, you would get a head node, you would get storage. On your head node, you would get a job scheduler, and then you would get compute nodes as well. The only difference is that for your compute nodes on AWS, they will be able to scale in and scale out depending on the resources that are required by the job scheduler on the head node. Now, the great thing about the AWS HPC connector is that it comes with a data transfer agent. So if you have a job that has their data only on the on-premise storage, and if Nice EnginFrame decides to burst that job into AWS, it will automatically transfer your data to AWS as well, so that that job will run on AWS without any issues. So you can see that Nice EnginFrame provides you really a seamless experience throughout submitting a job and go on until cloud bursting or however you want to use nice EnginFrame with AWS HPC connector. Now, I want to show you how easy it is to register a cluster on AWS through nice EnginFrame and use it. So here you can see the administrator view of a nice EnginFrame interface. You click on register, and that will bring you a pop-up which looks something like this. And you will have to upload or write a YAML-based code that is the configuration file for AWS ParallelCluster. Now, I'm not going to go into the details of the YAML file, but it's a very simple YAML-based text where you specify the resources you are trying to you want to deploy on your AWS account. Now, once you click on register here, your AWS configuration, AWS ParallelCluster configuration will be registered on EnginFrame. And once you have registered it, you will be able to create the cluster. And in here, you can click on Create Cluster, and in general, it will take you 5 to 10 minutes to deploy an HPC cluster on AWS. Now, depending on how you write the configuration, it could take a little bit longer, but in general, that's the time you should be expecting. Now, once you have your cluster created, you will see your cluster in ready status, and you will then be able to share your cluster with your end users. You will have the ability to share it with only administrators or all of your users or select a group of users. Choose whatever you like and click on Save, and that will ensure that you share your cluster with your respective users. Now, I also want to show you how a user would see the cluster from their side. And here you have an application template. So let's assume you have created an application template for OpenFOAM. And what the users will see is this part in the middle. In the middle, they would see 2 clusters. One is an on-premise cluster, the other is AWS. They would be able to choose from one of them and fill in the rest of the form and submit their job into the cluster that they are intending to submit the cluster, the job to. So this is an example of how you can give the users a choice of where they want to run their jobs. But if you remember the action script that I showed you earlier, you could also define more complicated things in there. For example, you could write a logic in your action script saying that whenever there are 100 queued jobs that are not running in your on-premise system, you burst your jobs into AWS. So it really gives you a lot of flexibility to manage both on-premise and cloud. Now I want to move on to the summary. So the benefits of nice EnginFrame and AWS HPC connector are that it seamlessly extends your on-premise resources to AWS. It has a single interface for on-premise and cloud, and it takes care of your data transfers as well. And it provides you easy access to a broad range of cloud-based services. So it's really about accelerating your research and innovation. Now, if you want to know more, we do have a booth here at Suntec City. If you're in Singapore and have a pass, please come visit us. We're running a demo there where we are running OpenFOAM with nice EnginFrame on AWS. And we're also visualizing the results over the same interface. We're also showcasing another solution there with our partner PBS Pro, with our partner Altair, where we are cloud bursting PBS Pro jobs into AWS as well, which is another way of extending your on-premise resources to AWS. If you have any questions, please feel free to reach out to me over this email address. And thank you very much for listening in for this talk.
Thank you, Shun, for this insightful talk. I believe at the moment being able to extend your on-premise HPC into the cloud is very, very useful. So our next talk is by Mr. Bill Bryce, VP of Product Management from Altair. And the title is The Convergence of HPC and ML AI, Accelerating AI with HPC. Mr. Bryce, please go ahead.
Hello, everyone. My name is Bill Bryce, and I am a Senior VP of Product Management here at Altair. Today, I will be discussing the convergence of high-performance computing and artificial intelligence and machine learning. At the beginning of this presentation, I have one slide to introduce Altair. There is much more that Altair Engineering does, and you can learn more by visiting our website at altair.com. The rest of the agenda doesn't really require much explanation, and at the end of this presentation, I will discuss what's next, since this is just an introduction to what you can do with HPC and AI/ML. So before I delve into the topic of this presentation, I just wanted to present one slide to introduce Altair Engineering. We have been doing HPC for a very long time. Products such as Altair PBS Pro and Altair Grid Engine are installed on millions of cores and thousands of clusters all over the world. Our customers use our products as part of their key innovation platforms, designing vehicles, rockets, aircraft, computer chips, and many other products. The convergence of HPC and AI/ML has been going on for several years, and there are many research groups who are currently using HPC with AI/ML, but it has always been more of an academic endeavor and a bit too complicated for the average machine learning user. Hopefully this presentation interests you enough to go out and do some more research on your own. Artificial intelligence and machine learning is a very large space, as you can see from the diagram. You can peel back the AI/ML space much like an onion from the outside in. The first layer, which is called AI here in the diagram, is really related to knowledge bases, which contain lots of data relevant to the areas you wish to predict using AI/ML. A good example of a knowledge base is an expert system. It uses reasoning, logic, and human knowledge. The system can use that information to make predictions or diagnosis. The next layer in is machine learning. And this represents normally traditional machine learning techniques that have been around for quite a while. In fact, many of these were originally part of statistics and optimization up until very recently. They are now expanded and used in machine learning, techniques such as gradient descent algorithms or even decision trees. Next layer in is representation learning, and it is a superset of deep learning. Whereas deep learning uses multiple deep network layers of abstraction, usually using artificial neurons, representation learning is more focused on feature identification and usually requires humans to assist or even identify the features. Finally, deep learning is the last layer. With deep learning, the system can be supervised, partially supervised, or completely automatic. Deep learning systems attempt to mimic real neuron networks that are present in nature and in the human brain. When I started creating this presentation, it was not clear to me the scope and breadth of machine learning techniques. So I set out to find a reasonable listing of artificial intelligence and machine learning algorithms. This is what I came up with, and it's based on sort of things I cobbled together from the internet. Broadly, you can split AI/ML into two distinct branches: the classical learning, much of it from probability and statistics, linear algebra and functions, and the newer techniques such as deep learning and reinforcement learning. As mentioned, these classical techniques have been around for a long time. We just didn't call most of these techniques machine learning. If we spend some time on the left side, you should see some algorithms that are a bit familiar, especially if you paid attention in your mathematics classes. Regression is probably the most well-known machine learning technique for the average person, because we all did some of this in high school. Clustering is also likely an approach that intuitively people can understand, but may not be familiar with. On the right-hand side of this map, ensemble methods, reinforcement learning, and deep learning neural networks are present. These newer approaches are not as familiar, and frankly, the mathematics can get very detailed and beyond the layperson. You need to study these techniques well to understand them. So clearly, there are many different approaches to artificial intelligence and machine learning, and this leads to many questions. One question we will look at on the next slide is, what are real-world applications of AI/ML? Today, AI/ML is used in many fields. On the left side are applications of classical machine learning. Some of these, such as identifying market trends, loan applications, and risks, are used daily, and you have likely experienced these yourself. Spam filtering is quite a famous and very useful application of machine learning. It isn't always perfect, but a simple perusal of your spam folder in Google Mail will convince you that it is useful. Healthcare is a long-time user of different machine learning techniques, some successful and others not so much. Modern uses of machine learning, such as tumor detection and illness prediction, are becoming very common. In fact, there are several companies that have commercial diagnosis services, which use AI/ML along with other statistical techniques. On the right-hand side of this slide are deep learning techniques. And in many ways, these techniques, when applied appropriately, deliver the most astounding, almost magical results. Common application of deep learning is autonomous driving. While we don't have 100% self-driving vehicles, the progress using deep learning has been quite remarkable. I recently was exposed to deep learning as it applied to summarization and paraphrasing of text. My daughter, who is in high school, has to write essays for several of her subjects. And I noticed that some of her vocabulary and sentence structure was a little different. This piqued my interest, and after discussing with her, she finally admitted that she took several of her paragraphs that she wrote and put them into QuillBot. QuillBot is a deep learning and natural language processing system that will rephrase entire sentences and paragraphs while maintaining the original meaning. One obvious question that immediately came to mind was, is this cheating? Well, probably not, since the human still has to read the resulting output, understand it, and place it into the context of the entire essay. But it is definitely a powerful tool and does make the teacher's job that much harder. Other common deep learning applications are satellite image data processing, financial fraud detection, and playing games like chess, Go, and even popular video games. As we saw in the previous slide, AI/ML can be used in many different industries. But what ML techniques work well with HPC environments? I wasn't sure which ML techniques worked well, so I needed some data and a little bit of analysis in Excel to at least have an idea of what techniques are common. Fortunately, the internet is full of information. You just have to search for it. I found this information at Kaggle.com, which is a machine learning and data science community. Many people upload datasets, code, use the tools, and perform analysis on the data in Kaggle. I found a good data set for the Machine Learning and Data Science Survey 2021. So this is pretty recent data that we're using. And the results are very interesting, as you can see from the bar graph on this slide. The data set contains 25,973 responses. So I'm reasonably confident that it is accurate. From the data, it is clear that classical machine learning is still the most popular approach used. The first three are linear or logistic regression, decision trees, or random forests, and then gradient boosting algorithms. So even though there are lots of AI/ML approaches and algorithms, the traditional ones are still the most popular. However, just after the first three, you can see that convolutional neural networks, dense neural networks, those are the deep learning ones, and the Bayesian type of machine learning are the next three. So this result where the traditional machine learning algorithms are more popular could be just because the machine learning practitioners are not as comfortable with the new techniques yet. We'll basically have to examine results of future surveys over the next several years to see if the deep learning techniques will become more popular. Machine learning is definitely a complicated field, and it becomes even more complicated because we're using computers, clusters of computers, software frameworks, and tools that we may not be familiar with to perform the machine learning. It definitely requires a significant investment of time to become proficient in machine learning. And typically an AI/ML engineer or scientist is not a data processing or IT expert. In fact, the computer IT part really just complicates things for them. With that in mind, most AI/ML scientists look for tools and development environments to simplify the process of using AI/ML tools and frameworks. Hiding much of the details below these tools, That then allows them to think about the problems they are trying to solve and not, the messiness of the infrastructure. Once again, using the machine learning and data science survey dataset from Kaggle, we can graph the most popular software integrated development environments for AI/ML. It is interesting that number one by far is Jupyter Notebooks. But again, that's probably not a surprise and may be skewed in this data set. It may be a bias because Kaggle makes it easy to use Jupyter Notebooks in their data sets and tools. The next two are Microsoft Visual Studio Code and JetBrains PyCharm. Visual Studio Code and PyCharm are very popular tools for all types of development. So again, probably not a surprise that they're also popular for AI/ML, especially since they're well integrated with the Python programming language, which is often used in AI/ML. IDEs really do simplify the process of using ML tools. And these IDEs have been integrated with some HPC tools. For example, you can see from the bar chart that the RStudio IDE is number 5 on the list of most used IDE. Altair recently integrated the RStudio IDE with Altair Grid Engine, making it trivial to run large batch workload on an HPC cluster directly from the RStudio environment with a few mouse clicks. If we dig a little deeper into the graph, you can clearly see that many people still prefer to use basic editors for their work. Notepad, Sublime, Vim, and Emacs are still used, but certainly not as much as the integrated development environments. On the previous slides from the Kaggle data, we learned that traditional or classical machine learning techniques are still very commonly used. But why is this so? Well, it turns out it's because of the structure of the data. In the table below, we have clearly defined rows and, more importantly, clearly defined columns with known ranges for the values in the columns. These ranges can be discrete or continuous, as most of the values are in this table. But critically, the columns match very well to features in machine learning. This data set is already labeled and features have been identified. The next very good reason is the amount of data. It turns out that more sophisticated AI/ML techniques such as deep learning require very large data sets to work well. Many data sets are just not that large. In this example that I'm showing you here in this slide, it has hundreds of rows of data, not millions or even billions. So deep learning is not really a good approach here. So the structure and the amount of data dictate the use of classical machine learning techniques in this case. But why does it fit well with HPC? Again, it is the structure of the data. HPC systems and HPC workload management systems, like Grid Engine and PBS Pro, apply very well to tabular data. You can create large batch jobs to process the whole data set. Or, in many cases, you can even split this data into groups of columns, or even rows in some cases, and process those columns or rows of data in parallel across a cluster of machines. So well-structured data, but not too much, works very well in traditional HPC cluster environments. So now that we know that you can use some ML algorithms, specifically the classical ones, and they fit well within HPC clusters and with our workload management solutions from Altair. But what does a typical AI/ML pipeline with an HPC cluster, a thing like using Grid Engine or PBS Pro, look like? Well, first of all, let me say that a typical pipeline does not necessarily have two separate stages, as in this diagram. If you're doing it without workload management, there's usually one. But because we're showing how you would do it with an HPC cluster, there is one for training and the other for prediction. So when you want to batch the training, you need that separate training stage that can be run on the HPC machine or cluster. The training stage of the workflow can be split up using workload management concepts such as array jobs or even parallel jobs. Simple models like linear regression and decision trees can be parameterized and run in a cluster of HPC machines, dramatically speeding up the training process. Additionally, if the data set is too large to fit into a single machine, it too can be split up and parallelized on a cluster of HPC machines. One of the important items to remember is that in order to really achieve speed up when using a tool like Grid Engine or PBS Pro, these workload management tools, you need enough data and a training algorithm that can split up the training data in order to be effective. Because if your computation you're doing in each one of these machines is too small, it may just be better to do it on one machine. Many AI/ML problems really don't have this kind of situation. So they don't necessarily need an HPC cluster. But when you do have a certain sort of medium-sized amount of data, not big enough that you're requiring deep learning, and you can split it up, then an ML algorithm that parallelizes well works really great on an HPC cluster. Let's dig a little deeper. We look at the pipeline. We want to know a little more about why ML training and why the specific classical techniques work well. I talked about linear ML models, and these can be parameterized and then distributed in parallel across a cluster of machines using standard HPC tools such as array jobs. Other things like individual decision trees can also be run in batch mode on an HPC cluster, but you're not going to get a lot of benefit just running sort of an individual decision tree. However, if you sort of extend this approach of training and you have many hundreds of decision trees or even thousands and using things like random forests, then you can see that using an HPC workload manager makes sense because each decision tree can be computed on a compute node in the HPC cluster in parallel. Another area where HPC can be of benefit is in hyperparameter tuning. Again, not a new idea. It's somewhat similar to the concept of design of experiments, which is a tried and true technique used in Altair simulation tools. If you randomize the configuration of these hyperparameters, this generates sets of hyperparameter configurations that can be run in parallel across the HPC cluster. Even more sophisticated techniques such as hyperband, where there are multiple brackets of hyperparameter configuration, can be run in parallel across a cluster. These types of techniques train the models better and faster than trivial techniques. Over on the right side of this slide, if you have a data set that cannot fit into the largest machine you have, it may be possible to partition this data set and place each partition on a different machine in the cluster. In this scenario, an HPC workload manager can do the heavy lifting of running and managing each machine participating in the ML training. Partitioning data is not as simple as just chopping it up, and frameworks have been created, such as the Cocoa framework mentioned in this slide, that can partition the data and run the computation. Finally, it is important to note that the line at the bottom of this slide, you may not require this sort of HPC cluster environment because most of these AML problems are smaller. They fit within a single machine. They use things like Spark and actually don't require an HPC workload manager. From all the previous slides, it's pretty clear that HPC workload managers such as Grid Engine and PBS Pro can be utilized in an AML pipeline, especially the classic ML algorithms. One of the interesting things we discussed is that until an ML problem is sort of big enough, most people won't need to use an HPC cluster with a workload management system. Their problems may fit well into one single machine. In this slide, I summarize an example approach to AML distributed training using Altair PBS Pro. As you can see from the list of software components, many different layers of software need to be installed and configured before you can even get to the point of using an ML training framework like Cocoa. I believe this is probably the biggest reason why workload management systems are not as common in AML pipelines than other tools. Workload management systems can be used for distributed training, but you need a deeper understanding of the workload management system itself and the additional tools such as Spark in order to use these components in a pipeline. And frankly, many data scientists and engineers do not have this experience, time, or the background to do it. So they use the tools that are already packaged and the easiest to use, and that is typically not the HPC cluster. But if you install PBS Pro and Spark, then connect PBS Pro to Spark so that Spark can submit Spark jobs to PBS Pro cluster, then use a framework like Cocoa with that, the whole environment becomes much easier. In fact, you shouldn't have to change things within Cocoa if you do this. As long as Spark is connected to PBS Pro, things should just work out of the box. However, I sort of mentioned this before, installing and managing an HPC cluster using PBS Pro is not a normal activity for an AML researcher. The best thing you could do is find an HPC administrator who manages the HPC cluster and have them install it, configure it for you. Then just use the software. Finally, as you can see on this slide, the Cocoa framework has built-in support for many different distributed training models. So it's likely that you don't have to implement your own. You could just use one of these built-in training models. So we're almost at the end of my presentation. And if we look back at the slides, we can conclude that HPC workload managers like Altair Grid Engine and Altair PBS Pro are very powerful tools, but are complex to administer and install. AIML practitioners usually don't even know these tools exist, And you really don't get the value out of using something like a workload management tool like PBS Pro or Grid Engine until the problem is big enough. Talked about that a lot. We also now know that traditional classic AIML algorithms fit well within the HPC cluster computing model. You can speed up ML training using distributed ML training techniques and frameworks like the Cocoa framework mentioned in this presentation. You can even partition some of the data and use distributed computing to speed up the training that way, again with the correct frameworks and tools. But there's still at least a couple of open questions, probably more. I didn't actually demonstrate a distributed training algorithm in this presentation, but I did explain what components are needed to achieve this. Also in this presentation, I focused on classic ML techniques, and I did not discuss if any deep learning, Bayesian or convolutional or reinforcement learning algorithms can take advantage of HPC workload management systems. So there's definitely more investigation needed. So in this presentation, I discussed Altair workload management tools, but we also have other products that are specifically designed for AIML. And for more information about those, please have a look at our website at altair.com. That's it for today. Thank you everyone for listening to my presentation, and I hope you found it very useful.
Thank you, Mr. Bill Bryce, for your insight from Altair's perspective. Indeed, AI and ML are very, very important because it's used almost everywhere. But let's head on to our next talk. I'm calling up Alan Lee to present his talk with the title High Performance Computing, The Journey Forward from AMD. Mr. Lee, go ahead.
Thank you. Let's see. All right, so hi, I'm Alan Lee. I'm the founder and head of AMD Research, and I'm a pure mathematician by training, quant by choice, and a computer architect by accident. Today I'm going to talk to you about architecting our future through HPC. So building is our nature. From the most basic of tools to the largest supercomputers, humans enjoy creating things, and it's just a foundational part of who we are. Now, in HPC, there are multiple levels of building. We build HPC systems that in turn are used to build solutions for a better world. At AMD, HPC comprises technologies at multiple scales and types, from laptops to supercomputers. So I guess I can take this off. From laptops to supercomputers, and from, say, scientific computing and AI to graphics and visualization. Building a better world is challenging, right? Silicon scaling is slowing, and the cost of advanced silicon is increasing. The diagram on the left shows how we're falling off the pace of Moore's law when it comes to new manufacturing technology. And the cost per unit area of advanced silicon is increasing as device sizes are decreasing. We're also resource constrained. Modern HPC, of course, requires more data, more compute power, et cetera. And the chart that you see here shows the increase in the number of parameters for a class of machine learning models. And it's actually doubling every 2.3 months. And we reached the 1 trillion parameter threshold early in 2021. Now, in addition to that, compute requirements are doubling every 3.4 months. So we have a big problem on our hands, whether it's from manufacturing or from the growth of the resources necessary. So in today's agenda, I'm going to talk about how do we tackle these problems. And I'm going to do it with using a building analogy. I'm going to start out with some technologies, which are the foundation in our toolkit. I'm going to talk about data as a resource, actually a natural resource for HPC. I'm going to talk about applications and workloads as our blueprints. And then I'm going to conclude with some innovations that are going to take HPC into our future. So here's the 7 technologies I'm going to talk about in our toolbox. We have heterogeneity, modularity, self-similarity, intelligence, acceleration, hybridization, and abstraction. So heterogeneity is the use of different types of compute elements within a single system. And it's important because you need to be able to combine different types of compute. HPC requires, in many cases, for a given workload, different types of compute resources. You need to be able to bring them to bear on a common problem. So if you look at this chart, you'll see that general purpose cores, or CPUs, they have a very broad applicability, right? However, in general, they tend to have a lower power efficiency, whereas different types of cores, whether it's GPUs or ASICs or adaptive computing elements such as FPGAs, they have a much narrower range of applicability. However, they have much higher power efficiency, for those applications in which they're actually designed. It's by combining, through heterogeneity, these different types of cores that we can achieve a robust system that has both high performance and meets the power efficiency that we need. Sorry for the blinding colors on this slide, but modularity is the ability to mix and match different components. Now, in a perfect world, we could simply create systems for any particular type of workload that we were interested in, but that's not economically feasible. So instead, we have to be able to put different parts from different things together at different times. Maybe it's for a particular upgrade path. Maybe it's because we have parts that are developed on different technology nodes. And this enables reuse in an upgrade. Now at AMD, we leverage modularity at different scales. In fact, we've been pioneers of modular design approaches at scales ranging from chiplets to packages to even platforms. Next technology in our toolbox is self-similarity, which is the quality of acting or appearing exactly or approximately the same at different scales. In terms of tools, this is optimizing for scale invariance. Now, the important thing about self-similarity to understand is that you have to understand the regimes in which it holds versus the extremes where it can break down. Now, the value of self-similarity comes from managing complexity through structure. Here's an example of self-similar design. You see in orange and the blue the different colors of data management units and compute units for a hierarchical system. And self-similar designs enable you to create scalable hardware solutions, manage the complexity that came from heterogeneity, one of our previous technologies, and enable parallel software constructs throughout the hierarchy. Next, I want to talk about intelligence. Now, intelligence can be defined as, roughly, the ability to acquire and apply knowledge. And at AMD, we not only use artificial intelligence, we use artificial intelligence to create more artificial intelligence. In fact, we use machine learning techniques to do software optimizations, to create microarchitectural enhancements, and even to do wiring on our chips. Acceleration is the next technology that I want to talk about. And it can be defined as using basically specialized hardware or software constructs in order to speed up applications. Now, there's different types of thinking. There are different types of data and compute in the world, and each have their own unique compute characteristics. And you have to map those characteristics of your application appropriately to the accelerators in order to get the type of both acceleration and efficiency that you want to use. Next topic will be hybridization. Hybridization is a technology where essentially you're combining or merging in some way what are traditionally disparate compute elements, such as compute and memory. These days, data movement is a real problem for high-performance computing. But one thing that we can actually do is we can include arithmetic logic units within the memory chips themselves, a technique called processing in memory. And this can reduce both latency and congestion in the network. Not only can we do this at scales like for processing in memory, but also can do this in the more abstract sense from the point of view of software and algorithms, and even at the system level. And the final technology I'll discuss in our toolbox is abstraction. And that's the focus on, concepts over implementation. And again, this can exist at different levels, whether it's more programmable domains, increasing heterogeneity, or higher data movement costs. And what abstraction does is it frees the programmer from the bonds, really, of the hardware, enables them to focus on the areas which are most important to them. So data. Data is really the natural resource of HPC. It can come in many styles, shapes, structures, and formats, each of which is important in its own way. You know, every day now in the world, we generate and store more data than actually we have in the entire 500 years between the advent of the printing press and the first computer, the ENIAC. And these massive waves of data clearly causing problems for high-performance computing. You have compute demands from over 3.8 billion users. You have network demands from the rising number of interconnected devices. And you have storage demands just from the absolute amount of data. And this is actually swamping many traditional HPC infrastructures as we start to try to solve the problems. So what can we do? Well, the important point is you don't want to drown. You want to consider, okay, well, what are we doing with these large-scale data systems? And really, the amount of data that we're dealing with is monstrous. And a lot of it is context-related, and it's ubiquitous, and it's coming from sensors, and it's coming from social platforms, and it's coming from information networks. And we have to understand how to handle this. We'll draw this analogy, drowning. What you actually want to do is surf. What you want to do is ride the tide of data. You want to harness its power, right? Imagine an analogy, you could be an expert swimmer, but you could still be crushed by a giant wave, right? However, with the help of a very simple tool, a surfboard, you can actually ride the tide to success. Similarly, you can be an absolute expert in HPC. What you want to do is take on board and assimilate the modern tools of data science in order to ride that tide to success. So the data landscape, of course, has been changing for a long time. And now we have things like data lakes and other types of constructs, which are important, again, for dealing with unstructured, contextually related data. And in addition to these new data management policies and structures, we're also considering and have been revisiting a lot traditional thoughts around databases, whether it's the relation of data or the synchronicity involved. For instance, we have storage optimized, which could be column-oriented databases, low latency serving, which could be key value and data stores, multi-relational databases, which could be graph databases, and schema flexible, which the usual way to think of that is document storage. Now, big data drives the need for big compute. That's what I mean by this. Well, over the last 10 years, if you think of supercomputing versus HPC, versus large-scale enterprise computation, those lines have really been blurred. And so in this talk, I'm just going to lump all those together under the rubric of what we'll call big compute. Now, in addition to those lines blurring, really there's been a convergence of big data, what I just defined in terms of big compute, and artificial intelligence and machine learning on two fronts. One is on infrastructure, and the other is on implementation. Related to infrastructure, you have virtualization, you have serverless computing, you have MPI techniques that have been brought over from HPC. And on the implementation side of the house, you have parallel file systems, you have artificial intelligence, and even RDMA fabrics that are coming into play. To get down a little bit more in terms of details, let's view the interrelationship now between high-performance computing and AI. First, we'll talk about what is HPC doing for AI? Well, these days, AI is repurposing many traditional high-performance computing engines for its own work, in addition to leveraging the high-speed interconnect networks and things like MPI that came from HPC, and also adopting software stacks, such as our own AMD's ROCm stack, the Radium Open Compute Stack, which is frequently used for HPC, now being more and more used for AI and ML applications. On the flip side of that, you have AI, which is informing HPC with intelligent workflows, dynamic job scheduling, inference co-processing, in-situ data analysis. And one of the most interesting things is actually using AI techniques for parameter estimation in traditional HPC. So here's something that we had done, some work we'd done on AMD research, was on some pressure modeling work. But the important part of this isn't really the application. What it does is that we took communication, said, okay, this is an important part of this HPC application. And rather than doing it in the standard way, we approximated it with some AI algorithms. And the AI approximation ran approximately two times faster, so half the execution time. But the important thing is we maintained the simulation accuracy. If you can see the diagram, I guess, in the center there, you see that's the base case with no ML prediction. And the diagram on the far right shows what happened when we actually used the ML-based prediction. And they're essentially indistinguishable from one another. And we're seeing this more and more, how HPC is informing AI, and how AI, on the other hand, is informing HPC techniques. So now let's talk about applications, and they're really our blueprints, they should be our blueprints for HPC. Sure, we have architecture diagrams, and we have interconnect topologies, and we have design schematics. When you think about it, if you really want to architect an HPC system, you have to start with the workloads that that system is going to perform. And the workloads of the future are going to require both big data and big compute. Now, this is obvious in the standard sense of scientific computing, but there's a lot new and interesting workloads on the scene that have many similar characteristics. That includes IT or information technology, includes logistics, includes finance, big data analytics, immersive computing, and even software-defined systems. So I'm going to start with information technology. You know, information these days and data in itself, it's a critical resource for business. And this is no more obvious in looking at the local IT department in most technology companies. It used to be that they served primarily a simple support function. But now they're business partners in actually using this data to find strategic insights. And that's critical because data is not just a resource, but for many companies, it is the most valuable resource for the business to get ahead. And when you're considering any valuable resource for a company like this, you want your supply of that resource to be maintained. You want it to be reliable. All of us are familiar with the semiconductor shortage going on right now. You need to look no further than that as an example. We think about data, you also need to create reliable infrastructures that are going to guarantee that support, both in terms of the immediacy and in terms of the long-term availability. Security and privacy is another area which is just ripe for differentiation based on new big compute architectures, both from the point of view of enterprise data, but also personal data. You know, as we increase the number of users and as we increase the number of devices, the threat surface, right, which is available to attackers increases. And this in turn increases the need for a substantial amount of computation. Now, this computation could be used for modeling or simulation of threats, AI-assisted intrusion detection. One of my favorite examples, though, is homomorphic encryption. Homomorphic encryption is actually the ability to manipulate data in its encrypted state without having to decrypt it. And this is extraordinarily valuable because one company could use another company's data without actually understanding what it is and having to decrypt it, which engages that privacy. But the interesting thing about homomorphic encryption, although it provides these security and privacy features, it is currently extraordinarily compute intensive. So let's talk about logistics. So let's see, the Port of Singapore over here is actually the maritime capital of the world. It is the second largest port in terms of tonnage, and it transships 1/3 of the shipping containers actually worldwide. Thousands of ships connect the Port of Singapore to 600 other ports in 123 countries in over 6 continents worldwide. But you know what? None of this is possible without logistics, the science of having the right resource at the right place at the right time. And the interesting thing about logistics as a discipline or a science is that it suffers from basically exponential or combinatorial explosion due to the type of problems that exist. In fact, common problems such as people have heard of, such as the transportation problem, right? The vehicle routing problem, these are all NP hard, meaning that they're extraordinarily hard to solve on traditional computing systems. Turning to finance, my personal favorite subject, if logistics is the foundation of modern economies, then finance is really the penthouse. It oversees and controls the economic world as we know it. And more, with more players and more global players, big data and big compute are really the future of modern finance. In terms of this slide, as I was putting it together, and I just put the picture down, and I was creating my little table of, hey, what are the elements that go into quantitative finance these days? And a friend of mine rang my apartment and said, hey, you got to get down here in 2 minutes because we're going to dinner. So I really quick just ran as quick as I could, and I filled out the table, and I put 16 things in there. Those are the things you see right there that are used in modern quantitative finance. When I came back after dinner, after a good night of conversation, enjoying with my friends, I was thinking, well, should I add some other applications to the table? And then I looked at this table and I said, you know what? If you look at this, and even without much squinting or without much blurring, you see these are the exact same 16 things that one could say about looking at the domain of medicine or computational fluid dynamics. We only need some minor changes. Of course, in my particular case, quantitative finance is my favorite, so I continue going back to that. So now I've talked about the technologies in our toolkit. I've talked about data as a natural resource for HPC, and I've talked about classes of applications. But now I really want to get to the heart of the matter, and what most people are interested in is what are really the innovations that are going to help build our HPC future. The first one I'll discuss is cityscapes. Now, I happen to live in the United States of America, and I've lived both in Texas and in Los Angeles. And when you have a lot of space to spread out, your cities become these long, flat, two-dimensional expanses, such as Los Angeles, such as Houston, Texas, right? However, when you have resource constraints, such as, say, land, you don't have enough land, or you're surrounded by water, or you have mountains on one side, you need to build up, because you need to put as much qualitative goodness into any unit area that you possibly can in terms of efficiency. Now, we've done the same thing in silicon for a long time. Even AMD, other companies that I've worked at, you continue to put more features, more value into every little bit of real estate that you possibly can. But eventually, you reach the law of diminishing returns. And we've reached that in silicon already. So what we've done is started to build up into 2.5D with interposers, into 3-dimension stacking chips on top of each other. In fact, AMD, just earlier in 2021, created their AMD 3D V-cache technology, which stacks caches right directly on top of a processor. Now, this is interesting, and it's very good, and it works extraordinarily well, but it really is just the beginning. It's like creating, okay, well, we've created a 2- or 3-story office building, and that's interesting, but it's really not the future of where we can take this. We can take all different types of heterogeneous processors and modularity and combine them in multiple stacks and things, and that will really be the future of high-performance computing in order to have the highest performance at the at the maximum power efficiency. Hybridization is something that's only going to increase in the future. Whether it's compute, storage, and interconnect, those lines are definitely going to be blurred over the course of the next 5 to 10 years. And we're going to need new programming models in order to achieve the maximum efficiency of these new hybrid systems. Photonics, also extraordinarily interesting. And photonics now, we've been moving things electrically. Now we can move things, with light. It can greatly improve the latency and, again, the energy efficiency of our systems. So, when I think of photonics, I really think of photonics in the context of where it can take us. In terms of where we are today, they're expecting that, say, a fiber optic cable by the end of this decade will be able to move 1 terabyte per second of data, which is about 2 orders of magnitude faster than the fastest PCI can today, right? But now you think of, well, gosh, how can we combine photonics with the other elements such as cityscape and hybridization and put all of these things together in a wild variety of combinations which are really going to push the limits of HPC and even what we mean by HPC moving into the rest of this decade and beyond. So quantum computing, I'll just touch on, briefly. There's different qubit implementations. You can use ions, you can use atoms, you can use photons, and they each have their own science behind them and the physics behind them, and they each have their own economics behind them as well. At AMD, we're treating quantum computing initially as an accelerator towards classical computing. So what are quantum capabilities? Well, in 1994, Peter Shor published his algorithm. It's called Shor's algorithm. He's at MIT right now, which is basically the ability to factor large integers. You can do that in polynomial time on a quantum computer, and that's faster than any known algorithm that can run on a traditional computer these days. Well, before that even, Richard Feynman said, you know what? When he was thinking and positing about what quantum computers could do, he said, it seems like we could probably use quantum computers to do well and to study quantum chemistry. And that turns out to be true as well. More interesting, and just in 2018, I guess, correlation, which actually stands for Fourier correlation. It is not surprising if you haven't heard what that is. Very few people have. It's actually a test problem, but the interesting is that Raz and Tal proved that there are actually two, well, I should say that BQP, which is a quantum complexity class, is actually distinct from pH, which is a standard polynomial complexity class. You'd say, okay, well, what does that mean? And so in plain English terms, so it's actually far easier to understand, but not nearly as rigorous. What this means is there will always be at least one problem correlation where quantum computing will be more efficient than traditional computing, no matter what the size and no matter what happens with traditional computing. But here's the real caveats. So most problems are still solved faster today on classical computers. And by most, I mean 99.9999% of problems. Also, a crossover, it's not going to be magic unless something happens in quantum complexity or traditional complexity theory that no one has predicted yet. But rather, it's going to be a grind. One algorithm after another algorithm. These other things will eventually fall. For some applications, quantum computing is going to be faster, and for others, traditional computing is still going to hold sway at least far into the foreseeable future. And I'm going to end this again by getting back to effective abstractions. And I think when I wrote this slide, I don't know, maybe I was in a negative mood, but I was thinking, oh, we're shielding developers, right, from the underlying hardware and the danger it might cause. But as I started thinking about this, flying on the plane over here, I believe these abstractions is really something far more positive. What these abstractions are doing is enabling programmers, enabling scientists, whether they're biologists or whether they're metallurgists or whether they're working on mechanical engineering or civil engineering problems, to basically be separate from the HPC system itself and really focus on their domains of expertise to solve problems that are important for the rest of the world. So, in conclusion, we build HPC to build a better world. And what we need is more talented people building HPC technologies, participating in HPC, architecting HPC solutions, and that will make the world a better place. So thank you very much for your time, and I really appreciate the opportunity to speak to you today.
Thank you, Mr. Alan Lee, for this really great talk about the future and the journey forward for AMD. And just like that, we came to the last speaker in this session for today. Dr. Huang Jingquan will talk about global innovation trends in high-performance computing. Please.
Thank you, Chairman. Very good evening, a very good afternoon, very good morning, if you're listening to this from the other part of the world. My name is Jing Quan. I take care of the patent analytics team at IPOS International. So if you look at the title of my job and also my company, you would know that I am not an expert in high-performance computing. Neither do I know much about quantum computing. So today, my talk comes from a very unique perspective. Which is patents filed by organizations worldwide. I sincerely hope that you will find my talks useful. Hopefully, it will validate some of your hypotheses, assumptions, and more importantly, it will provide you with new insights. As a start, just a short introduction of the IP Office of Singapore and IPOS International, the organization I work for. IPOS is actually under the Ministry of Law of the Singapore government. As the National IP Office, IPOS administers IP laws, promotes IP awareness, and provides infrastructure of the IP development in Singapore. IPOS International, the organization I work for, is actually the expertise and enterprise engagement arm of IPOS. So together with IPOS, we support enterprise to grow using IP. Specifically for my team, we work very closely with government agencies, organizations. We provide them with data-supported, evidence-based recommendations to help them shape their R&D directions and business strategies. What we specialize in is called patent analytics. Now, many of you would have known that patents is a form of IP that companies seek to protect their inventions. More often than not, patents represent most of the R&D. More often than not, most of the R&D innovations are actually first reviewed in patents. So patents, as a result, represent a vast source of information covering the frontier of the technology development in almost all technical fields. So when we aggregate a large amount of patent data of similar nature, we will be able to discover relationships and trends. So for example, if we look at all the patents relating to artificial intelligence published in the last 10 years, we will be able to see who are the top companies, who are the leading countries, what are the latest AI techniques, and latest area for application. We can also look at patents originating from one country, for example, Singapore, to be able to assess what are our local research capabilities. And equally, we can look at all patents filed by one company, Facebook, for example. We can examine all the metaverse inventions they already have before, when they change their name to Meta. So today I'm very excited to talk to you about innovation trends relating to high-performance computing and quantum computing from the perspective of patents. So let's start from the high-level trend, the big picture. So the chart on the left, you will see that these are the global innovation trends relating to high-performance computing and quantum computing. From the number, you can see that inventions relating to high-performance computer, HPC in this case, is a lot higher than quantum computing. The high volume of actually close to 20,000 of them in the last 10 years and about 2,500 inventions in last year alone is really due to a few of factors. Number one, the barrier to entry, the cost of developing a HPC or maybe of owning a HPC is much lower as compared to quantum computing. Okay? By definition, HPC simply means aggregation of computing power. So a company can actually build their own HPC by simply putting more computer nodes together, or they can even purchase a powerful HPC off the shelf. And HPC innovations are also supported by advancement in both hardware and software. So when we talk about hardware, these days, the smallest feature size of semiconductor chip is about 4 to 5 nanometers. When we talk about new algorithms, more advanced algorithms, we often talk about artificial intelligence, machine learning. So all these enable companies across different industries to use HPC for various purposes. As for quantum computing, you can see that it's more a recent phenomenon. Most of the inventions occur only in the past 5 years, where the innovation started to surge in 2017. But the growth is really, really high. Okay? The CAGR rate, the compound annual growth rate, is about 40%. What that means is that in every 2 years, the number of inventions relating to quantum computing would double. Okay? But if you look at the overall volume, it's still at its initial stage. There's only less than 4,000 inventions worldwide relating to quantum computing. Many countries are active harnessing the power of high-performance computing. What I listed down here are the top 5 countries and their respective lead players based on number of inventions filed. Not surprising, you will see that among the top 5 are the 2 most powerful economies in the world, the US and China. We also see innovative nations like Japan, South Korea, Germany. Many of these have their big players, and many of the players are known to people who are very familiar in the computing industry. We have computer makers, computer companies like IBM, Fujitsu, Hitachi, and NEC. We also have software players, SAP, Microsoft, and Inspur from China. Okay, but if you look closely, you will see that the profile of companies in China is very different from the rest of the world, from its main competitors. Not many of you would expect State Grid Corporation of China to be the top of the list, and certainly not many of you would expect that the academic research plays such an important role in terms of HPC innovations. This is because in China, the research ecosystem is slightly different as compared to the rest of the world. Across different industries, based on the studies that we have done, the academic research plays a very important role in China. They have very strong government funding. They work closely with industry partners. They develop technologies for their SMEs. And in China, Chinese universities have one of the highest successful rate of company spin-off and startups. The top player in this case, the National University of Defense technology of China is no stranger to people who are in the supercomputing industry, because they have played a very important role in China's supercomputing development, starting from the early days in 1980s, where they helped to develop the Yinghe first generation, until now in the recent years, where they actually helped to develop Tianhe 2A supercomputer in China. So when it comes to high performance computing and supercomputing, the Chinese academic research is certainly a force to be reckoned with. And similarly, we can look at who are the top players, who are the top countries leading quantum computing research. Now we have a new player, actually new country, Canada, led by top companies like D-Wave as well as 1QB. Okay. But if you look at the numbers in detail, you will see that US is really in a much more advanced stage, and they have a significant edge over their competitors. The top player, IBM, for example, has close to 400 inventions, whereas other strong players like Intel, Microsoft, Google, they all have large portfolio over 100 inventions. Google in 2019 has in fact claimed to have achieved quantum supremacy. So what we noticed, a strong difference between HPC and quantum computing invention is that, if you recall, I mentioned in my first slide, quantum computing has about 4,000 inventions. And if you look at the number of inventions held by the top players, right, you will see that most of the inventions, about 30%, are actually held by the top 10 players. So what that really means is the quantum computing technologies are concentrated really at a handful of players. They are not accessible at this stage to the majority of players. On the other hand, if you look at high performance computing, you will see that the top 10 players only contribute to about 13%. That means most of the quantum high performance computing technologies are quite scattered, distributed across players, across different industries. And that's because many of the high performance computing technologies nowadays are developed for industry-specific applications. When we look at our data, close to 30% of the data set relating to high performance computing are meant for specific industry applications. On the other hand, when I look through closely the entire data set of quantum computing, I see less than 3% of the inventions out of the 4,000 that mentions applications. And when I look through the 3% in detail, most of them talk about applications briefly or in a very generic manner. So in summary, we can conclude that for quantum computing, we are still quite far away from seeing any actual applications. Most of the technologies at this stage focus on the system development, the quantum systems, the error corrections, and the cooling system as well. And the lack of industry-specific applications also shows that quantum computing is still at the initial technology development stage. So we have seen a lot of applications in using high-performance computing. So what are these? So I actually classified the 20,000 inventions relating to HPC according to the tech fields. So not surprising, most of them belong to computer technology. That's the nature of high-performance computing. But increasingly, we're also seeing more applications, more inventions are designed for purpose-specific functions, for example, control measurement. Apology for the small font size, but if you look at the last honeycomb, which says IT methods for management, that's where you see a lot of applications of high-performance computing in finance, in e-commerce, in insurance, and that's where you see companies like Alibaba, Amazon, and Ping An Technologies. Okay. Increasingly, we also see high-performance computing that are used across other industries such as medical technology, transportation. A high percentage, I would say a major use of high-performance computing in medtech is actually high-performance image processing for medical diagnosis. In addition, high-performance computing also used for disease modeling and treatment. One invention, for example, filed by Hitoshi, focused on using HPC to determine the dosage regime for particle beam therapy for cancer treatment. Now, for the dosage regime for cancer treatment is very important because under dosage in this case would mean a very low efficacy, whereas overdosage would cause severe adverse effect. Okay? So high performance computing in this case play a very nice role in terms of accurately determining what is the best dosage regime. Transportation, we have seen autonomous vehicles, drones, and this is a space where we see lots of use of high performance computers by car manufacturers such as BMW, Audi, Toyota. We also see increasingly high performance computing also used in the car infotainment systems, for example, by lead players such as Robot Bosch. In fact, when I look through the whole data, we are seeing that high performance computing is already applied across virtually all industries and all technology sectors. Even for some of the sectors with small innovations, small number of inventions such as pharmaceuticals, high performance computing are already being extensively used for drug discovery. Okay? For environmental technology, for example, HPC are used to monitor and regulate the operations of chemical plants. Okay? And the best example to me for fusion between high performance computing and AI can be best illustrated using this curve. Okay? AI is certainly a big topic these days and is also commonly mentioned in many of the computer technology conference. So we have started monitoring AI about 7 years ago, and we have seen how China has catch up and overtaken US in terms of number of AI inventions. This chart shows you the number of AI inventions that mentions the use of HPC. Okay, you can see from the chart it's actually going up very fast. In summary, about 1 in every 10 artificial inventions actually mention the use of high performance computing. So you can see that HPC really play an integral role in supporting the development of AI. The chart on the right shows you the top players. What I want to highlight is actually the top players actually make an even heavier use of high performance computing when developing AI. IBM, for example, has close to 3,000 inventions that effectively translate into 1 in every 3 of their inventions makes use of high performance computing. Okay. And as an illustration, maybe to see how HPC are used for different purpose, it can be best demonstrated from a user perspective. Okay. So here I have the example of the State Grid Corporation of China. Okay. Just a background, State Grid Corporation of China is the world's largest electric utility companies. Okay. It's also the second largest company in the world by revenue. It has close to 1 million employees and it services more than 1 billion customers. When we look at our data, it's actually among the global top innovators in both AI and HPC. Okay. Just like many of the proactive or maybe forward-looking companies, SGCC has started their digitalization journey many years earlier, and they're strongly backed by the Chinese government to transform their electric grid into a smart grid. And they have the ambition to develop technologies and set standards so that other part of the world can actually use their standards. Okay. Some of the examples I highlighted here, again, apologies for the small font size, actually the use of HPC by SGCC. Okay. So for example, high performance computing are used extensively for monitoring of their grid for fault inspection and isolation. They are also increasingly used for prediction and forecast in terms of the electricity demand, both short-term and long-term. And another area of major use of HPC is actually to optimize the energy distribution and redistribution, especially in view of the fact that increasingly now renewable energies are used as part of the grid. So we have seen a lot of solar farms, a lot of wind farms in China, and HPC in this case play a very important role in terms of making sure optimizing the distribution and redistribution. Okay. So the last part of my talk is another observation that we have not exactly quantum computing per se, but something related to, but something highly relevant, which is post-quantum cryptography. Okay. The mechanism of our current day's encryption actually relies on one of three hard mathematical problems. One of them is integer factorization. The other two are discrete logarithm and elliptic curve discrete logarithm. All these three hard mathematical problems, right, can be easily solved by a powerful enough supercomputer. Quantum computer. So what it really means, our current encryption system will fail in the face of a powerful quantum computer. Okay. Well, even though at the current stage, publicly known experimental quantum computer still lacks the kind of processing power to break any real cryptographic algorithm, many cryptographers are actually designing new algorithms just to prepare for the time when quantum computing become a real threat. Okay, so this is also captured in the patenting trend in the world, so which is shown on the chart on the left. Okay, so a lot of inventions are appearing in most recent 3 years, and if you ignore the contribution from the top player, Ruban Quantum Technology, you will see that the trend is going up very consistently. On the right, I highlighted some of the top players. The number one player is actually Ruban Quantum Technology from China. They have a very high number of 132 inventions. We also see top players like Intel, PQ Shield from UK, other companies like Siemens, Daimler. But we noticed that a large portion of it actually comes from the academic research, mostly from China. Shenzhen Polytechnic, for example, Chinese Academy of Sciences, Fuzhou University, and Xi'an University. So the large presence of academic research shows that this is still in an early phase of development, and it remains very interesting to see how post-quantum cryptography will further evolve and how this will play out when they race against the development of quantum computing. So with that, I have come to the end of my presentation. Thank you so much for your attention, and thanks once again for the wonderful opportunity to speak here. Thank you.
Okay. Thank you, Dr. Huang Jinchuan. So just 2 items of housekeeping. When you exit the hall, please return the silent conference sets. Those tiny black boxes just outside. And for those that tuned in virtually, there will be a Q code displayed any moment now, where you can leave the feedback on today's session, on today's speakers. And please let us know what we did well, what we didn't do so well. And with that, I'm closing this session, and I'm inviting you to tune in tomorrow at 1:30 p.m. Thank you so much.